Hi, everyone. Thanks for stopping by. My name is Scott, for those of you who don't know me, and a lot of the work I'm going to discuss with today was done in Reza Shadmir's lab at Johns Hopkins, but I've actually recently transitioned to Adam Hampman's group, and so we'll be doing some mouse neurophysiology over the next couple of years. The work I'm going to talk about today is about sensory motor adaptation and some ideas about how it's supported by a competition between parallel adaptive systems. So this project is the culmination of work done by many collaborators across many different institutions, and it's really important that I start off by recognizing them. So at Johns Hopkins in Reza Shadmir's lab, myself, obviously Reza, and a very talented, well, was an undergraduate at the time, but is now on his way to medical school, Jihoon Jang. Friends down in Argentina in the De La Maggiore lab, Gonzalo and Valeria. Up north of us in Canada, we have at York, Denise, Shana, and Marius, and then last but not least, a couple other friends at Johns Hopkins, Adrian Heath and John Krakauer. Okay, so without any further ado, I'd like to start off by considering an example of something that I think most of us do or have done, or at least familiar with during pre-pandemic times, and that's bowling. So when you're bowling, you have to start any given throw by making a decision, and that is you're going to make a cognitive decision about where you're going to aim the ball. So you may decide to aim straight towards the head pin, or let's say off to the left or to the right. At the same time, your brain is sensing properties about the bowling ball, for example, its mass, and it's using those properties to determine subconsciously a set of muscle activity patterns that are going to then activate your muscles in order to throw the ball down the lane. So the throw is a culmination of both a cognitive decision and then subconscious activation of your muscles. So suppose on this particular throw, there are a couple outcomes that you observe. First, you may miss the pins a little bit to the left. And secondly, maybe you saw that not enough, many pins fell down, indicating that you didn't have enough power behind the ball. So you may make some choices due to these observations. So first, you may decide to change where you aim. Because you missed on the left the last time, this time you might decide to aim a little bit more to the right. And because you didn't hit many pins down, you may decide to put a little bit more power behind the ball. So you might upgrade to a ball with a larger mass, in this case, let's say 15 pounds. Now, of course, on top of this decision, this 15-pound ball is going to be sensed by the brain, and it's going to produce a different set of muscle activity patterns, in this case, larger ones, in order to actuate your arm and move the ball, again, down the line. So what I'm trying to illustrate here is that when we make an action, we observe an outcome of that action, and given that outcome, we make a series of changes to our behavior, which we call adaptation. And so this adaptation is supported both by subconscious systems, and I'm going to term this today implicit learning. So implicit means subconscious parts of adaptation that you don't control and are potentially unaware of. And secondly, conscious choices that you make. These are strategies you might use that we'll call explicit learning. So explicit learning is the same thing as strategy. Okay, so how do these systems work together to improve behavior? That's what we are going to consider today. Okay, so in the lab, the way that we measure implicit and explicit learning is something like this. So people come in, they're holding on to a robotic manipulatum, and their arm is hidden underneath the screen. And they see a visual display, something like this, where they're told to reach from a starting location to a target location. But because they can't see their arm, they're given a cursor, in this case shown by this little black dot, which represents the position of the hand. And they're told they have to move it from the starting position to the target. So the experiments start off with a baseline period where the cursor just follows the hand exactly. And different reaching trajectories might look something like this. That would be one movement, a second movement, and a third movement. And each time the cursor hits the target, the participants awarded a point, in this case represented by their score. So what we do in these experiments is we track behavior. We track what the subject's doing. In this case, we can summarize what the subject's doing by measuring their reaching angle. This is the angle that the hand is making in between the cursor and the hand's trajectory. And so every time I say reaching angle, this is the angle I'm referring to. And what we do is we can track that over the course of different trials. So during this baseline period, when nothing particularly interesting is happening, participants tend to reach straight to the target, in this case represented by 0. So their hand moves straight to the target. Then we do something a little bit more interesting. We impose a perturbation, in this case a rotation. Now when people are going to reach straight to the target, their cursor is going to be rotated relative to the direction the hand is moving. So when the hand is moving straight to the target, in this case, the cursor is going to be rotated by a fixed 30 degrees, and participants are going to have to adapt to that rotation. So the first couple of trials might look something like this. The hand is moving straight to the target, but the cursor is moving off to the side. And then the participant would learn to counter-rotate their reaching angle in order to bring the cursor back to the target. So then they're again scoring points. And so If we track again the reaching angle over the course of the adaptation process, we get a learning curve. And the learning curve in this experiment looks something like this. You start from baseline behavior, and then you gradually adapt to try to compensate for the rotation, in this case about 26 degrees. Now, given what I talked about on the previous slide, we know that this adaptation is supported by multiple things, which we can broadly dichotomize as implicit and explicit components of memory. So some parts of the adaptation are intentional, and some parts of them are subconscious. So the way to think about that is in the following diagram. Suppose you're trying to reach straight to the target, and you know there's a rotation pushing to the right. So you may decide that you shouldn't aim at the target, but you should aim a little bit to the left, like in our bowling example. But where your hand actually goes is not exactly where you planned on aiming it, because there are also implicit corrections that your brain is making to the hand's trajectory. So the total reaching angle, or where the hand goes, is really the sum of this explicit strategy and then this implicit redirection. So that is what this total reaching angle is composed of here. How might we then measure these two systems independently? Well, one idea, well, there are many ways to do this, but the way that we're going to do this today in the different experiments I'm going to talk about is we're just going to tell people to stop aiming. So we're going to say on this trial, there's not going to be any feedback. We want you to move your hand straight to the target, don't re-aim. And so when we tell people to stop aiming, what we can measure is their hand still might not go exactly to the target, but any deviation that's now happening between the hand and the target is not due to a strategy, which the participants are no longer using, but these implicit corrections. And so by telling people to stop aiming, we can independently measure directly this implicit system. So in this experiment, when we told people to stop aiming, we'll watch the reaching angle precipitously and immediately drops. And what remains after this instruction is the part of learning that the participants can't control. And that would be the implicit memory. And the part of the memory that the participants could control, that they were strategizing and turn off, is just the remainder here, and that is the explicit strategy. So we have implicit learning and explicit strategy, which we can tell apart, we can tease apart by telling people just to not use their strategies at different moments in time. Okay, so what we're going to talk about for the first half of this talk is how these implicit and explicit components of adaptation respond to different features of a perturbation, in this case, the size of the rotation, which is a central question in motor learning. So for this, I'm going to employ some data that was reported from Neville and Cressman in 2018. And in this study, Neville and Cressman tested participants in different rotation conditions. So one group adapted to a 20-degree rotation shown here, another group adapted to a 40-degree rotation, and a third group adapted to a 60-degree rotation. So 3 different rotation sizes. Neville and Cressman then told participants to stop aiming. They measured the residual amount of adaptation, and the drop in learning from pre to post instruction is total explicit strategy across these 3 rotation conditions. So when Neville and Cressman considered what changed across these 3 rotation conditions, they saw that the strategies that people used in the 20-degree rotation, the 40-degree rotation, and the 60-degree rotation gradually increased, which is intuitive, right? When you have a large rotation that's large error, you're going to use a different conscious strategy, a larger conscious strategy to try to reduce that error. But what was surprising is that though strategies that people use got larger as the perturbations grew in magnitude, the implicit learning that the participants couldn't control remained roughly the same. It actually didn't increase the rotation, which is a puzzling effect. Why doesn't the implicit learning system increase when the rotation is low? And so this is really the question that we're going to be talking about during the first half of this talk. What might be causing the saturated phenotype in the implicit learning system? So to get at that, it's really helpful to have a simple model that can help us understand why implicit or any learning system for that matter might saturate in the first place. And so the models that we employ are simple state-based models. These are trial-by-trial models of motor adaptation. What we're doing is we are trying to understand how a motor behavior, in this case, perhaps a reaching angle, changes as a function of trial over time. So during the beginning of experiment, you start off in a baseline condition. You're producing a 0, quote unquote, motor behavior. And what we're trying to do is we're trying to use a state-based model to understand how this movement is changing over time. So we have a movement measured on trial n, and we have the next movement measured on trial n+1, and we want to know how it changes. So the reason why it changes is you introduce a perturbation. So for us, this is a rotation, and that rotation causes an error. The difference between what the perturbation is and what you are doing is this error, and that error drives learning or changes in behavior. So we add a term to our model where it represents error-based learning. In this case, this term right here. So the error term here is E of n, which is the error on trial n. And we multiply this term by another variable called B, or error sensitivity. And what error sensitivity is just how sensitive you are to an error. Where an individual that has low error sensitivity would adapt very little from one trial to the next due to a given error, And an individual, a large error sensitivity would be the opposite. They would be very sensitive to that error, and they'd update their behavior a lot and learn more rapidly. But there's another really important feature of adaptation, and that's that if you find a way to remove errors, so you somehow clamp errors to 0, or you remove feedback that you have people continuing to reach, what happens is that people do not just continue to persist in the memory they previously had. That memory actually decays in the absence of error. And so to account for this forgetting, what we do is we add another term to our model, a retention factor. And this retention factor is shown right here. It's a number less than 1, and it represents how this memory is going to decay from one trial to the next. Okay, so this is a very simplistic model that helps us account for how behavior changes from one trial to the next during adaptation. But it's not exactly clear why this model produces steady state behavior. And just to remind you, that's really what we're after. We want to understand why implicit learning exhibits steady states that might saturate for different rotation strategies. And so to explain why this might be, it's helpful to derive some equations. And to do that, I think rather than show you slides, it's most helpful for me to just very briefly switch over to OneNote and to just derive this equation over the next couple minutes that we're going to be using for the remainder of the talk today, so that we're all on the same page about where these things come from. Okay, so we have our state-based model of learning, and we're trying to understand why this model saturates. So what we have to first start off is we have to realize that this is just a state of learning. What we care about is the implicit state of learning. So I'm going to give all of these terms here a little subscript I, except for our error, which stands for the implicit system. We're trying to model implicit learning here. The first step we have is to think about this error source here. We have to come up with what exactly is this error. Well, that's already nicely drawn out for us over here on the left. The error is just the difference between the rotation and what your action is on a given trial. So if the rotation is, let's say, 30 degrees, and you're producing an action of 15 degrees, that's going to leave an error of 15 degrees. 30 minus 15 is 15. So an error on a given trial N is simply the rotation minus someone's total action, which is X of N. Sorry, and I didn't say this, but R is just the rotation. So this is just a number. You can think about it as, for example, 30 degrees, 40 degrees, so on and so forth. Okay, so error is just the difference between the rotation and total reaching angle. And as we've already talked about, this total reaching angle X is really composed of two different systems. It's composed of an implicit component, X sub I on trial N, and an explicit strategy, X sub E on trial N. And these two things are both going to determine the total reaching angle. So what I can then do is I can re-express my error, E sub N, as really the rotation minus this X here, which is then just subtracting off these two components of learning. And then what I'm going to do is I'm going to take this error and I'm going to insert it up into the error expression here in the state-based model. And so what we're going to get is we're going to get X sub I on trial N plus 1 is equal to the retention factor times X sub I on trial N plus B sub I times our error, which is R minus X sub I of N minus X sub E of N, as we just showed. Okay. Now what we're just going to do is we're going to combine some terms. We're going to take this X sub I out and we're going to move it next to this X sub I right there. And then we're going to then be able to simplify just slightly and say X sub I on trial N plus 1 is equal to A sub I minus B sub I times the current implicit learning plus B sub I times R minus X sub E of N. Okay, so we're almost done. We have to just take one last step here. And that's that we have to understand saturation. So these models have a nice property that they saturate. So over time, the system is going to asymptotically approach a steady state. And so we're going to refer to this steady state as X sub I of SS, the implicit steady state. And what you notice is that when the system reaches a steady state, by definition, it no longer changes. So the implicit system on trial N is the same thing as the implicit system on trial N plus 1, and for all future moments in time. And so they're all just equal to steady state implicit learning. So we can just make this substitution into our equation that we derived on here. I'm going to take all of my X sub I's right here and here, and I'm going to replace that with just steady state implicit learning. And I'm going to replace my X sub E with your steady state explicit strategy. So when I make that change, you're going to get X sub I steady state equals A sub I minus B sub I times X sub I steady state plus B sub I times R minus X sub E steady state. And last but very not least, I'm just going to do the algebra for you. I'm going to solve for Xi steady state. And what you would get is Xi steady state after a couple algebraic steps is just B sub I over 1 minus a sub I plus b sub I times r minus x sub e s s. So this is the very important equation of the day, which I'm going to refer to as the competition equation for reasons that will become clear in a moment. So now you can see where this equation comes from. It comes from starting with the state-based model, which posits that learning is due to forgetting and also learning from error. You write out an expression for that error, which is in terms of a perturbation. And we have to know that what we're doing on a given trial is the sum of implicit and explicit learning. And then last but not least, we simply have to write out a steady state condition. Combining these different points of relatively intuitive information together then yields this equation here, which is how we can predict how much implicit learning will occur over the long run in terms of the quantities you see on the right side of this equation. Okay, so now jumping back to the slides, let's talk about this equation. So it may look slightly involved, but it's actually really simple. This equation is really the product of two important terms that have different qualitative meaning. So first, let's look at this term on the right. So steady state implicit learning is altered by a term that appears on the right here. And this is the driving force for implicit learning. So it may seem that what's driving learning is the rotation, which is in some sense true, but really what's driving learning is not the rotation, it's error. And so the error that's driving learning is the error that remains after a strategy, x sub e, has partially compensated for rotation. So again, if you had a 30-degree rotation and you had a 20-degree strategy, that 20-degree strategy is only going to leave 10 degrees of error left to drive implicit learning. And that's the idea of this driving force. So it is the difference between the rotation and one's explicit strategy. Then we have the term on the left here. This term on the left is simply a learning gain. B and A are simply just numbers between 0 and 1. So this term here, this quotient, is also between 0 and 1. And it just is a gain that describes how sensitive the implicit system is going to be to its driving force. So if this gain was, let's say, 0.5, the implicit system would learn 50% of its driving force. If it was 0.75, it would learn 75% of its driving force, so on and so forth. That's how to understand this equation. We can more simply just write this, therefore, as that implicit steady state learning is simply proportional, i.e. you have a learning gain here, P sub I, to the difference between the rotation and one's steady state explicit strategy. And we're going to refer to this as the competition equation. And we're going to call it the competition equation because what we can see is that these systems will exhibit a competition between explicit and implicit learning, right? As explicit strategies get larger, the driving force for implicit learning is going to get smaller, and therefore implicit learning is going to get smaller. So because of this negative sign here, implicit and explicit systems will exhibit this antagonistic behavior because they're trying to accomplish the same thing together and sharing a resource. Okay, so why did I go through all this? Well, the reason why I went through all this is to try to relate this steady state implicit learning predictions to the process of saturation that we talked about before. So Neville and Cressman measured implicit learning across 3 different rotation sizes and saw that the implicit system was the same across these 3 different rotation sizes. And what we're wondering is maybe is this saturation somehow related to this competition as described by this model? Okay, so how might we do that? Okay, so again, to just reiterate, 3 different rotation conditions, but relatively similar amounts of implicit learning across these 3 rotations. So how might a competition model produce such a behavior? So we're going to consider 3 different scenarios. So the first scenario is that strategies are growing, as we know they are, at the same rate as the rotation. So if I were to plot explicit strategies as a function of rotation magnitude, which you can see here, you're going to get a line with slope 1. Because as the explicit strategies are rotations increasing, your explicit strategies are increasing at the same rate. So you have a slope 1. So what we need to know, though, to understand implicit learning is the driving force, basically the difference between this rotation and your explicit strategy. So in this case, where these 2 quantities are increasing at the same rate, their difference, r minus x sub e, which is driving implicit learning, is actually going to remain constant. So even though the rotation is getting larger, this driving force is staying the same. Okay, if the driving force is staying the same, this r minus x sub e, the competition model is going to suggest that the implicit learning system is also going to stay flat. Even though the rotation is getting larger, its driving force is staying the same, ergo it's going to have similar amounts of learning across the 2 different rotation conditions. Okay, secondly, we may have a scenario where strategies are growing at a slower rate than the rotation. If your strategies grow at a slower rate than the rotation does, what's going to happen is the driving force is going to get larger over time. So the larger and larger the rotation gets, the more driving force there will be for implicit learning. And so implicit learning will go up as the rotation gets larger. And to complete the trifecta, you can have the case where strategies are growing at a faster rate than the rotation. So in this case, you'd have a faster rate than the rotation, a slope that is greater than 1. If the strategies grow faster than the rotation, what's going to happen is this driving force is going to decrease over time, or not over time, but rather over rotation size. And therefore, as the rotation gets larger, they're actually going to get less implicit learning. So 3 different phenotypes are possible. So which of these is true for the Neville and Cressman data set? So the critical directions, what you have to consider is the difference between the rotation and one's explicit strategy. So when we looked at that across these 3 different adaptation conditions, what we found is that they were actually constant, or roughly constant. That when you move from a 20-degree to a 40-degree to a 60-degree rotation, the driving force for implicit learning in this experiment was actually similar. So the model predicted that implicit learning should actually saturate across rotation sizes. So you can start to develop the intuition for how a composition model like this would produce a saturated phenotype of implicit learning. Okay. So interim summary, adaptation is supported by parallel implicit, which are subconscious, and explicit strategic systems. When perturbations get larger, strategies increase, but sometimes implicit learning stays the same as we see in this Neville and Cressman data set. Why does the implicit system exhibit saturation behavior? One hypothesis is that the implicit system isn't responding to the perturbation, but the error that's remaining after your strategy has partially compensated for the rotation. So in this competition model, when strategies grow at the same rate as the perturbation, the driving force for implicit learning remains constant. And indeed, the data exhibited this property as the rotation increased from 20 to 60 degrees. The error between the rotation and the participant strategy remained the same. And so in the competition model standpoint, this created an illusion that the implicit system's response had saturated, when in actuality, it's just the driving force that had saturated. Okay, so if we're right about this, the key prediction is that we can release the implicit system from the saturated phenotype if we somehow reduce the rate of growth of explicit strategies. So if we slow explicit strategy growth, we should allow the implicit system to grow as rotations get larger. So how might we test that? So Shana, Marius, and Denise did an experiment where they adapted individuals to an abrupt rotation. So this is very similar to the Neville and Cressman data. So in this case, it's a 60-degree rotation, and the rotation just abruptly turns on. It goes from 0 to 60. And this would be the learning curve associated with that abrupt rotation. So you don't have to do the rotation all at once. So Shana tested another group of participants, in this case in a stepwise condition, where the rotation first increased to 15 degrees, 30 degrees, 45 degrees, and then 60 degrees. And so what adaptation looks like in this more gradual condition is it looks like it is completed in a bunch of steps. First, one jump, second jump, third jump, all the way up then to the 60-degree rotation. So what is the point of this? Well, one nice feature of doing this perturbation gradually is the following. When the rotation is imposed abruptly, what happens is the errors start really large. They're going to start at 60 degrees and they're going to decline over time. Remember, error is simply just the difference between the rotation and the learning curve. So it's really just the space in between these curves, or the space in between these curves right here. So errors are large when you have an abrupt perturbation, but when you do the perturbation gradually, what happens is the errors start off much smaller at 15 degrees, and then they remain small over time. And so because of that, the difference is in that in abrupt adaptation, you'll have large errors with respect to gradual adaptation. And why that's important is that our explicit strategies key into these errors. When there is a large error, a large discrepancy, we tend to use larger strategies than when there are smaller errors. And so the idea here is by perturbing people gradually or in steps, what you can do is you could mitigate explicit awareness of the rotation and decrease explicit strategy. And that is what they attempted to measure by measuring strategies at the very end of the experiment. And they found indeed that in the stepwise condition where errors were smaller, these explicit strategies dropped by about 10 degrees. So if we go back to the competition equation, this competition equation would predict that when strategies get smaller in the gradual condition here, this driving force is going to get larger, and therefore implicit learning is actually going to increase. And indeed, that is what they measured in the data set, that by perturbing people gradually, implicit learning increased because explicit strategies had decreased. Okay, so that is one thing I want to share. But the second really critical component to consider here is what is implicit learning doing as the rotation is getting larger and larger over time? All we considered here was just a 60-degree rotation period. But what about all the other 3 periods? So going back to Neville and Cressman for just a moment, remember that in the Neville and Cressman data set, perturbations occurred abruptly and strategies grew very quickly as the rotations got larger. And because strategies grew at the same rate as the rotation, the driving force for implicit learning stayed constant as the rotations got larger. And that caused implicit learning to exhibit, at least from the competition equation standpoint, a saturation in implicit adaptation. Okay, but what about in the gradual conditions used now by Denise's lab? Here, they're going to measure strategies at the end of each of these periods, and they find that because of the smaller errors, strategies are actually smaller. So they also increase as the rotations get larger, but you see that the rate of this increase is more slow. And so what that means is that when we look to see how the difference between the rotation and the strategy at any moment in time, or the driving force, here is actually going to increase with the rotation size. And so what the competition model predicts is that in this gradual condition, implicit learning should gradually increase as the rotations get larger. And indeed, that is what was measured in the experimental condition. So again, consistent with the competition equation. So just to recap, when you perturb people abruptly, what happens is that strategies are growing quickly as the rotations get larger. And because of this, the implicit learning system exhibits a saturated phenotype. However, when you perturb people gradually and the errors are smaller, your strategies increase more slowly as the rotation gets larger. And this leads to an implicit phenotype that scales as the rotation gets larger. So both of these two phenotypes of implicit learning are perfectly consistent with the competition. So if this is right, you can make a number of predictions, and we're going to explore three for the rest of the talk today. The first one being that implicit learning can decrease with rotation size with extremely rapid strategy growth. So here we talked about making strategies smaller and watching implicit learning increase. But if you were to measure conditions where strategies go really rapidly, we actually predict that implicit learning can come down instead of going up. Second thing we might predict is that if we force or influence people to use larger strategies, we're going to suppress their implicit learning. And the third thing is that if we look at individuals and we look at just their natural variations, some people that use larger strategies than other individuals, people that use larger natural strategies will inadvertently suppress their own implicit learning. And so we're going to check these three ideas over the remainder of this talk. So first things first, we're going to look at extremely rapid growth in strategies and how that alters implicit learning. Okay, so for this, we're considering data that was provided us by Jonathan Say and Rich Ivory's lab in their preprint from this year. So in this experiment, participants adapted to one of four different rotations, either a 15-degree rotation shown here, a 30-degree rotation, a 60-degree rotation, and then a very large rotation condition, a 90-degree rotation shown up here. And at the end of the experiment, they measured implicit and explicit distance by telling people to stop aiming, as per usual. Okay, so when they measured strategies during this no aiming period, what was observed is that as the rotation gets larger, strategies again also got larger, but the rates were actually different in this case. So when they moved from a 15 to a 30-degree rotation, the rate at which strategy increased was really slow, a slope of about 0.05, which is much less than 1. When you move from a 30-degree to a 60-degree rotation, the slope is larger. It's medium size. It's actually closer to 1. It's about 0.8. And when you move from a 60-degree to a 90-degree rotation in this experiment, the slope is really large. Strategies increase really large by a factor of about 1.8, so larger than 1 in this case. So just given everything we've been talking about so far, what you predict then in terms of driving force is that as you move from a 15-degree to a 30-degree rotation, because the strategies increase slowly, the driving force is going to go up. Then when you increase at a rate of approximately 1, the strategies are going to remain, the driving force is going to remain about the same. And then when you increase really rapidly with a rate of greater than 1, you're going to have a drop in the implicit learning driving force. And so this competition model simply predicts that your implicit learning should be just a scaled copy of the driving force, which is shown here in model predictions. And indeed, that is what was measured by Jonathan. So a case where implicit learning doesn't actually exhibit monotonic changes with increases in strategy, but also perfectly consistent again with the competition model. So again, we can find conditions here, this 60-degree to 90-degree rotation, where when the rotation increases and strategies go really rapidly, we can actually get drops in implicit learning, even though the rotations have gotten larger. Okay. So now we're going to move on to the second prediction, that if we force people to use larger strategies, we can suppress their implicit learning. And for this, we're going to go back and consider the Neville and Pressman experiments again. So the condition I told you about so far is a non-instructive condition where no trick-through is used in the adaptation process. People either experience a 20-degree rotation, a 40-degree rotation, or a 60-degree rotation. And when you measure strategies at the very end of this period, on average across these three different rotation sizes, strategies were about 20 degrees. But there was another condition that Neville and Cressman considered, and that was an instruction condition. Prior to experiencing the rotation, Neville and Cressman told participants that you're going to experience rotation. This is what's going to happen. And to compensate that rotation, you should aim off in this direction. And so people in this instructing condition used that information and adapted much more rapidly and completely to the rotation, which you can see here in the 20 degree, 4 degree, and 6 degree rotation. And unsurprisingly, this more rapid adaptation was supported by an increase in the strategies that were used. In this case, strategies increased by about 10 degrees. So what we would predict is that by forcing people or influencing them to use larger strategies, the competition model is actually going to have a decrease in the driving force for implicit learning. So the competition model is going to predict that in the instructing condition, implicit learning is going to drop. And indeed, that is the phenotype that was measured in these experiments. So again, by forcing people or influencing them to use larger strategies, you decrease the driving force for implicit learning, and you're therefore suppressing the implicit system. Okay, last but not least, we're going to look at a similar question, but just natural variation across subjects. And we're going to ask if individuals that naturally use larger strategies suppress their own implicit learning. And to get at this question, we're going to have to go back to the math just a little bit to come up with a model that can explain natural variations across individuals. So going back to this, the competition equation, the steady state model for implicit learning, remember that it's composed of two terms. We have a driving force, and what we spent most of our time talking about is the driving force so far, R minus the strategy, rotation minus strategy. What we haven't talked about so much is this other factor, the learning gain. All we've said is that it's a number between 0 and 1, and it depends on error sensitivity and retention. So if I just go and replace this learning gain, again, with just this variable p, and I multiply p into this difference here, r minus x of e, what we can see is that we arrive at the equation can be thought of as a line, where if your dependent variable is how much implicit learning an individual will exhibit, that variable y has a bias or an intercept that is your learning gain times the rotation. And then it's related to the slope minus the learning gain times your independent variable, the strategy that the individual uses for x. So y equals mx plus b. So again, this is a line with intercept p sub I times r and slope minus p sub I. So what this means is that if we were to measure somehow p sub I, we can exactly quantitatively make predictions about how implicit learning in a certain individual should vary with their explicit strategy. So if we measure this p sub I, we could then make quantitative predictions. And again, just going back and completing the circular logic here, p sub I is simply just the ratio of these two different quantities, which depend on error sensitivity and retention. So we're going to take this, and I'm just going to run this loop in reverse to explain what we're trying to do. So step one is imagine that we have a way to isolate implicit learning. I'll talk about that in a moment, but we're going to isolate implicit learning. Step two, once we have the isolated implicit learning curve, we're going to measure the retention factor and the error sensitivity that's associated with that implicit learning system. Once we have those two learning properties, we're going to measure p sub I, the implicit learning gain. Then what we can do is we can specify our linear model, which relates a person's strategy to their implicit adaptation. And then we can actually measure implicit learning and explicit learning in individuals and test this against the model prediction. Okay, so step one, isolate implicit learning. Okay, so what you see here is a normal rotation experiment, a 30-degree rotation experiment, and these is the adaptation curve. And what I haven't talked about so far is other quantities that you can measure during the adaptation process, in this case, preparation time. So there is a time between when a target is shown and then when the participant is going to begin their reaching movement. So it takes time to recognize where the target is in space and then to begin your movement. So during the baseline period, you can see that this preparation time is low, doesn't require much effort to locate the target and then reach. But when the rotation comes on, preparation times increase sharply. And this increase is due to changes in strategy. So when you are deciding to re-aim your reaching movement, you have to find a new target. That aiming process, that remapping, requires time. It requires a cognitive time of this rotation to occur. And so one idea is you can suppress explicit strategies by minimizing the time that people have to make these reaching movements. So in a separate condition, what we did is we suppressed preparation time. Anytime participants reached above their baseline reaching times, we penalize them to force them to not use additional time to prepare their movement in order to try to suppress their explicit strategy. And indeed, when we measure the learning curve under this limited reaction time condition, what we find is that the learning is substantially subdued because the strategies that are present in this black learning curve here are suppressed. How do I know that it is the strategies that are getting suppressed versus perhaps just the whole system, implicit and explicit learning, just scaling down? Well, we can measure. So at the very end of the experiment, we have a no aiming period where we tell people to stop aiming, to aim straight to the target. And as we've already discussed, the change in behavior from before and after this instruction tells you how much strategy there was. And what we can see is that in this limited preparation time condition, strategies were limited to a little bit less than 2 degrees, whereas in normal conditions where you don't limit strategies, you get about 12.5 degrees of implicit learning. What you can say here is that by suppressing preparation time, you can reduce explicit strategies by about 90% or so. So what we can say here is, to a first approximation, this red learning curve here is purified in implicit adaptation. So now that we have isolated implicit learning, we can go ahead and we can calculate the retention factor and the error sensitivity for this implicit learning curve here. I'm not going to go into the details about how you empirically do that, but suffice to say that during this no aiming period here, the implicit retention factor is related to the rate at which the memory is retained over this no feedback period. And so in this case, you can empirically estimate a decay factor that's 0.95. And then once you have this decay factor, you can go to the learning period and you can look to see how participants' behavior changes from one trial to the next, and then use that to empirically estimate how sensitive they are to error. So in this learning curve, it's about 0.1. So now that we've measured these implicit learning properties, we go to step 3. We're going to determine our implicit learning gain. The implicit learning gain, remember, is just B divided by 1 minus A plus B, shown up here at the right, which is approximately 0.7. So we know for this red learning curve that we predict an implicit learning gain about 0.7, and now we can use that to specify the model, the competition model. So for 30-degree rotation, that would look that an implicit strategy is 0.7 times the rotation, 30, minus someone's explicit strategy. And that makes a linear prediction that if I look at the implicit angles and the explicit angles across different participants, the model would predict that the data should fall along this particular line. The last thing we're going to do is we're going to go back to our unlimited preparation time condition, where there is both implicit and explicit learning, and we're going to measure those two quantities. So we also have these people stop aiming, and during this no aiming period, we measure how much learning was explicit and how much learning remained that was implicit. And we plot that in the same plot right here. We see that individual subjects match the model predictions very closely. So 2 things. First of all, when participants use larger explicit strategies, they tend to suppress or exhibit less implicit learning due to competition. And the predictions also fall along the model predictions that were measured in an entirely different set of conditions and subjects. Okay, so one last interim summary before we get to the last point here. Adaptation is supported by parallel implicit, so conscious and explicit systems. The implicit system can exhibit different phenotypes, a saturation or a scaling with rotation size. We found that these phenotypes could be explained by a competition with explicit strategy. And we use this equation to make and then confirm 3 predictions. First, we talked about how when strategies rapidly grow or at greater than a gain of 1, that we can actually measure decreases in implicit learning with rotation size. We saw that if we forced or influenced people to use larger explicit strategies, that it suppressed their implicit learning. And we also saw that individuals that naturally use more strategy have suppressed implicit learning. And what this last point really means is it means that someone's implicit system is responding to variability in strategy, a point that actually was made under random rotation conditions by the Smith lab last year. But what if we had it backwards? Could it also be that this relationship is running in reverse? What if these individual negative relationships between implicit and explicit learning are driven by the opposite causality direction? Could it be that it's not implicit learning that's compensating for variable strategy, it's that strategies are compensating for random variations in implicit learning? So we have implicit learning systems that are independent and variable across people, and strategies are simply compensating for those variations depending on the error that remains after you have implicit learning. So this is difficult to tease apart unless we go a little bit further. So to understand how we might tease apart these 2 scenarios, let's consider a simple thought experiment. So let's say we have 2 participants, participant A and participant B, and they have the same implicit learning parameters, but participant A has a better strategy. So what is clear in this case is that if you have the same implicit learning system, that you have a better strategy, that implicit learning in, total adaptation in participant A is going to be larger because it's simply just the sum of these 2 things. But on the flip side, because participant A has a better strategy, even though they have more overall adaptation, due to that competition mechanism, the greater strategy is going to leave a smaller error for the implicit system. So implicit learning system is going to be smaller. So let's put some numbers to this example. Suppose you have a 30-degree rotation. You have participant A, they use a strategy of 15 degrees. And you have participant B that uses a strategy of 10 degrees. Then we can go to our competition equation. Again, remember, suppose that these two individuals have the same implicit learning system, or for our purposes, they have the same implicit learning gain of 0.5, so 0.5 for P here. And now we can predict implicit learning. So in participant A, you're going to have 0.5 times 30 minus 15, or 7.5 degrees of implicit learning. And for participant B, you're going to have 10 degrees of implicit learning. If we sum together now explicit strategy and implicit learning for participant A, we're going to get 22.5 degrees. And for participant B, we're going to get 20 degrees. So this is exactly what we predicted above. We predicted that if implicit systems respond to variability in strategy, what's going to happen is that increases in strategy result in greater total adaptation. So the participant that uses a larger strategy is going to have more overall learning. However, the opposite is going to happen in the implicit system. The total adaptation is actually going to be associated with less implicit learning. So you can see that even though this individual learned less, participant B, they had more implicit learning than participant B. So I should say, without getting into it right now, I'll get into this in hopefully future little talks that I plan to just put on YouTube. This is really true on average. All of this really relies on the fact that participants A and B have the same implicit learning parameters. If they don't, all bets are off. And if you have a lot of variability in implicit learning parameters in the subject population, you may fail to detect, given statistical power, these decreases in implicit learning. But that is neither here nor there. That's a subject for a different time. Let's just consider the opposite. So here we talked about how in the implicit system is being driven by variability and strategy. The flip side hypothesis is that explicit strategies are driven by variability in implicit learning. So without going through all the rigmarole here of going through all these derivations again, you can just think about it as just take your I's and replace them with E's and take your E's and replace them with I's. You're just going to get the opposite. You're just going to get the opposite relationships. So you're going to see that if implicit learning is an independent system, people that have large implicit learning are going to exhibit more total adaptation. But that's going to leave a smaller target error to drive the explicit system. So individuals with larger total adaptation are going to be associated with less explicit strategy. So it's the same general ideas here, but just flip sign. Okay, so to hammer this point home, again, remember again, this is on average, but to hammer this point home, let's just consider what this looks like in simulation, right? So again, first idea is we have implicit systems that are exhibiting, they're independent and they're exhibiting variability across people. But critically, the explicit system is compensating for that variability. In such a case, you can also measure what looks to be a competition, this negative relationship between implicit learning and explicit strategy. However, what you would find is that there is a negative relationship between total adaptation and explicit learning, but a positive relationship between implicit learning and total adaptation, as we discussed on the previous slides. These equations come from the updates, the preprint that I will about. Okay. So although I'm not getting into it in this talk, you could think about this as an SPE learning model. This would be what you'd expect for a system that learns just based on sensory prediction errors, for those of you who might be familiar with this term. In these models, it's imagined that you have an implicit system that is independent and learn from this error source, and your explicit strategies just compensate for that independent implicit system. So this is what would have it in such a case. All right, but what we're talking about here is the competition model. And in this case, you have explicit systems that are variable across people, and you have implicit learning that is compensating for that variability. In this case, we're also going to measure a negative relationship between implicit learning and explicit adaptation. So this is that competition we've been talking about. But we're going to measure the opposite correlations here for total adaptation. So we're going to see that participants that have larger strategies will have more total learning. But we're going to see that more total learning is actually associated with less implicit adaptation. Okay, so now we're going to test these ideas in different subject populations. So we're going to look for conditions where we can see a negative relationship, a competition between implicit and explicit learning. So this would be the data that we've been looking at so far. These would be data collected in Oprah Johnson's lab, Dana Maresh, from Denise Enrique's group, which I talked about a little bit earlier in this presentation, and then lastly, data that was shared by Jonathan Say from the Ivory lab. So in all these cases, you have these nice strong relationships between implicit learning and explicit strategy, but we don't necessarily know where they come from. So one idea is that it's the implicit system that's compensating for variability in the explicit system. In this case, what we're going to predict is that if we look at total adaptation, that it's going to have a negative relationship with implicit learning, but it's going to have a positive relationship between strategy, and then vice versa. If we think about the ultimate model of this SPE model, where explicit strategies are compensating for variability in implicit learning, we're going to see that total versus implicit is going to be positive, and total versus explicit is going to be negative. So just the same idea here, but just flip something. Okay, so which of the two are okay? What we saw in each of these 4 experiments is supportive of the computation framework. These are our data. What we found is that as people that have more adaptive perturbation were actually associated with less implicit learning, but greater adaptation was supported by larger implicit strategies. That's consistent with competition. The same was true in the Danchin Labs data set, in Denise's data, which I talked about earlier, and then also in the data set that was provided by Jonathan Say. So in all these cases, implicit learning exhibiting negative relationships to total adaptation, a positive relationship between explicit learning and total adaptation. Okay, so for today's little segment, this is all I want to share with you. So I'd like to just talk about some conclusions. So the conclusions here are that adaptation is supported by parallel and implicit explicitisms, which you've heard me say many times at this point. This parallel organization between implicit and explicit learning can give the incorrect impression that these systems are independent of each other. But that is not necessarily true. On the other hand, because these two systems share a common error, they actually compete with each other, much like you might compete with a sibling of yours for the last slice of pizza. So when these two systems care solely about this common error in really simplistic scenarios, implicit learning is going to be governed by the competition equation, which I've talked about today. This equation explains why implicit learning can saturate when rotations get larger. And remember that this is because that when rotations grow, strategies grow. And if they grow at the same rate, implicit learning systems will exhibit a saturation. This equation explained why reducing strategies by mitigating awareness, that was the stepwise conditions tested by Denise's group, would allow implicit learning to grow. If we enhance strategies by coaching people, we're going to suppress implicit learning. If we have rapid strategy growth, we can actually hit these strange conditions where we have non-monotonic implicit behavior shown by Jonathan Say. And we also showed that individuals that have naturally variations in strategies, people that use large strategies, inadvertently suppress their own implicit. And this last point can create unintuitive scenarios where increases in adaptation are supported by more explicit strategy, but less implicit learning. And again, really should put some caveats here. More on this to say, but in a different way, where there are some cases where you actually need to do these relationships. Okay, last but not least, why is this important? So some of you probably study human psychophysics and motor learning. Some of you might not. So why might these ideas be important? Well, here we talk about behavior as a dichotomy between implicit and explicit systems, but there are many dichotomies in the brain that you could draw that would abide by similar principles. So one of these might be feed forward and feedback control. When we're making a movement, part of that movement is planned ahead of time, part of that movement is planned online, but both controllers want you to move accurately. And you may exhibit a competition, quote unquote, between these controllers because they both have the same goal, and that is to make you move accurately. You can also think about competition in terms of anatomical circuits. So as a rough approximation, if you think about the brain as consisting of different units anatomically, you may look at certain processes that happen in the cerebral cortex and other processes in the cerebellum that both try to service learning, but may compete with each other because they are trying to solve the same problem. Another thing which I didn't put in the slide here, but I had actually meant to add is goes back to Maurice Smith and the idea of the fast and slow learning systems. So different time scales of learning can actually compete with each other given the same thing. Okay, 2, these ideas call into question existing models that treat implicit and explicit systems as independent. And 3, and perhaps the most important part of I think this work is that what we're describing is that competition between implicit and explicit systems has to be considered when you investigate how these systems change over time or across different experimental conditions. So this makes up a huge bulk of what we do in the psychophysics community, right? We try to do condition A1 and condition A2 and measure how some part of behavior change, whether it be explicit learning or implicit learning or temporally labeled learning and so on and so forth, right? But what we are showing here is that if, let's say you do that, let's say you have 2 different conditions, different amounts of implicit learning in 2 different conditions, and you see a drop. That drop in implicit learning can be due to either one of 2 things. It could be bona fide impairments in the implicit circuit, right? So perhaps maybe condition 2 somehow changes the implicit system sensitivity to error, it drops. And that would, of course, cause the implicit learning system to learn this. However, it could also have nothing to do with the implicit system at all. It could be that explicit strategies got larger in these conditions, they changed, and that it indirectly changed the driving force of implicit learning. The implicit learning system is exactly the same, only what drives the implicit learning system. So we have to know in a given experiment if there is competition in the systems that we're considering, and if so, how much competition there is, and what is the marginal behavior of these two systems. And so it's not possible to just look at one system and know what that system has changed or not over time or over conditions just by considering it. You have to consider all of its other parts. And so a slightly subtler point, which I'll address more in a future presentation, is what happens if you do two conditions and you don't see a change in implicit learning. So this might make it seem like the implicit system is unchanging or inflexible, but it really doesn't necessarily mean that, right? Because the implicit learning system is changing not just because of the environment, but because of all the other co-systems that are also adapting, right? So it could be that the implicit system changed, but so did some other system, which just negated those changes. So it looked like the implicit system didn't change at all, but really its properties. Yeah, use the word change a lot there, I realize. If that's not super clear, I'll get more into that in future presentations. In particular, I'm going to talk about in the future savings, and this is treated in the preprint right now, which we've yet to update, but this is still present in the first preprint, though we've made a couple improvements with. But anyway, savings is a condition we're trying to measure systems across two environments, and we think that these rules that we're talking about today are actually really important to keep in mind when we measure this. Okay, last but not least, I want to list some limitations that we're going to talk about much more, or at least a little bit more, in what I hope to plan our future little presentations like this. So I apologize, I updated the presentation and that was the wrong slide. Okay, same thing. What are the limitations? So in our tasks, what we did is we had people aim for the target, and the cursor here, we tried to have them hit the target with the cursor. Okay, so in this condition, if there's a rotation moving you in the right direction, you may aim somewhere off the left. And in the experiments that we consider here, this aiming was not directed by any visual stimulus. It's just that you had to aim off the empty space in terms of like what feels right to you, what feels good relative to where the target is. So we showed in this case that there is a target error. So this is the error we've been talking about today. It's the difference between the cursor that you can see and the target you can see. And we showed across many scenarios that this target error seems to be really important for driving the implicit learning system. But there are other ways to do implicit adaptation. Sorry, getting ahead of myself. Before I get there, let's talk about our bowling example, right? So our bowling example is target errors here would be like where the ball goes relative to the pins. We want to hit the head pin, and the target error is where we are on either side of the head pin. Okay, but there could be other errors. There could be other targets and other errors, right? So in many forms of implicit learning that arise for various reasons, people give additional landmarks that the subjects can use for aiming, right? So when they're aiming, they're not just aiming to empty space, they're aiming to targets that they can fixate and that draw their attention, right? And so they're aiming to these targets. This would be something like in bowling, if you were to, and actually are on the lanes, these different markers that exist on the lanes. So imagine you use these markers, direct how you're going to aim the ball in order to hit the pins, right? So it actually turns out that when you have these aiming landmarks, there is another very strong error that's present. And this is called a sensor drift error, right? So this is an error that doesn't care about the primary target. It cares about the idea that you were aiming off here to this target. You would normally predict under normal circumstances that the cursor is going to move then towards the aiming target, but the cursor moved over here. And this would create a sensor drift error. And it's going to be very strong. So note that when you don't have these conditions, when you have conditions where you're aiming, but there is no target to reinforce that aiming, Taylor and Ivory showed about a decade ago that sensor drift error here is very small. And so actually this is a really nice direction for future work, but these SPEs themselves are really context dependent. They can be large and they can be small. And so we think that the reasons why in our work, when we consider these experiments right here, we were able to really capture behavior very well to the first approximation just with these target errors, probably because these sensor drift errors were small. However, all bets are off with these more complicated scenarios where you have multiple targets, each of them servicing adaptation. And for one of the most recent treatments of such a condition, I would recommend Jonathan Today's preprint that just came out that we presented at MLC. Okay, so with that, I just want to take just another second. I want to say that we really appreciate you taking the time to consider these ideas with us. I'm sure you have a lot of other things to do than just sit here and watch a YouTube lecture. The hope of doing this is that we want to provide a couple of short presentations about similar topics that are going to accompany what is now a preprint, but it's under review right now. I really should note that as of posting or recording this lecture, this is June 23rd, 2021, many ideas that I talked about in this presentation aren't actually in version 2 on bioRxiv yet. We have yet to update this. So stay tuned over the next couple of weeks for an update to this model v3, which is going to have a lot more than you probably want to read about some of these ideas that we have here. And I just want to give an illusion of if I make good on my hopes here. Topics that I'd like to also give short presentations like this on are how things like generalized or plan-based SVE learning relates to some of these ideas I present here. I want to talk more about savings and interference in the implicit system, and I'd like to also do a little bit more on subject-subject correlation. So these are just 3 things in no particular order that I'd like to also talk about in the future. But with that, again, I'd like to thank you for your time, and yeah, have a great day. Oh, I didn't put it here, but my email address, I'd love to hear from you, either if you have data that speaks for or against these ideas. If you want to email me at scottalbert1@gmail.com, I'd be happy to talk to you guys about some of these ideas in more depth, or just send them to you. Okay, thanks guys. I'll talk to you soon. All right, bye.